All right, hello. My name is Simon, and I am with Brian and Sam, and our topic is on the analysis of radial artery pulse using discrete Fourier transforms. So, a bit of an introduction here is that we are interested in the radial artery pulse diagnostics, which is an age-old method in traditional Chinese medicine, which entails evaluating a patient's health by looking at the pulse at the radial artery. According to TCM, the pulse is regarded as an important indicator of the internal condition of the body, offering important insights into the health of various organ systems. Because it is so close to the skin surface, the radial artery, which is found on the wrist, is easily accessible and frequently utilized for pulse diagnosis. Um, Practitioners can feel the radial pulse using their fingertips and observe characteristics such as the depth, strength, rhythm, and pace. Each of these characteristics is linked to many facets of health and can highlight abnormalities or imbalances in the body. So we found a study from or by Yang, Zhang, and Liu on radial artery pulse waveform analysis based on curve fitting and using discrete Fourier series. Their research suggested a unique discrete Fourier series approach for feature extraction from pulse waveforms. They handled the pulse waveform as if it were a signal made of several subcomponents, each represented by a sine and cosine signal with different amplitude and frequency. They also used least square regression to fit the average waveform for each sample using discrete Fourier series. The discrete and Fourier series functions coefficients make up the final feature vector, which offers a numerical depiction of the pulse waveform. So um, for this project, we are using the method that we are using is discrete Fourier transform, which is a mathematical approach that breaks down the periodic signals into their component frequencies by using DFT on radial pulse data. Important insights that might not be visible to our eyes can be extracted. By transforming the pulse waveform into its frequency domain representation, medical professionals can spot particular abnormalities or patterns that could point to underlying medical issues.
The data that we used for this project was the HeyMod or HeyMod Dynamic Modeling Research Group. They have a database of 3,325 virtual subjects, each with distinctive radial pulse waveforms based on several parameters. The dataset is a 1 by 3,325 cells, each consisting of 6 fields. We are only focused on two, which are one cycle and heart. The one cycle field has 4 columns, but from these four, we're only interested in time in seconds and pressure in PA. We use time and pressure for our analysis since we are interested in the pressure variable. Typical pulse shape. So to better understand our data, we graphed it so that time was on the x-axis and pressure was on the y-axis. The overall shapes seem to look very similar across all the subjects. However, the values may differ in a Fourier transfer, and we wanted to see if that was the case. Analysis strategy. So we wanted a way to categorize our patients into different groups, and we did so using the stroke volume. Each patient in the data has one of three stroke volumes: 66.4, 83, and 99.6. We compared the Fourier transformations of pulse for individuals with different stroke values using the FFT function in MATLAB. The Fourier transform contained a real and imaginary component. We looked at the differences between patients in both components.
We plotted both the real and imaginary component for each individual in the data set, and we found that for pretty much everyone in the real component, there is a large spike, much larger than all of the other values, around the middle. Um, and for the imaginaries, there is also a spike in the middle, just slightly to the left of this main spike, but it is a lot smaller. Um, so this was pretty much the same for everybody, so we couldn't really find any noticeable differences to the naked eye between individuals. So to sort of find a difference, we found the maximum value for the reals and imaginaries, or the coefficient at the tip of each of these peaks for each individual, and we found the average of that for each of the different groups of stroke volume. So here you can see our transform of one of the pulses, or of a pulse for the 6.4. As you can see in the red, there's the base of the large spike, and in the blue you can see the smaller spike as well. This is pretty much the same for all three graphs. And so we found that as the stroke volume increases, the average maximum value increases for both the reals and the imaginaries. And then we took the ratio between the imaginaries and the real coefficients, and we found that the three groups are different from each other. Um, so there's not a distinguishable pattern like there is with the coefficients for the maximums, but there is still some difference. So yeah, so in conclusion, we did find a difference in the groups with ratio and the average maximum, and there's a potential that doctors could be able to use this to predict what someone's stroke volume is. Um, and although we can see that there is a difference, we would suggest further investigation to check if it's statistically significant and to test its ability to predict stroke volume before it is used for that purpose. So these are the resources we used, and thank you for listening to our presentation.